In this question, we are given a pattern shown here where we can see some interference fringes and then the diffraction pattern as well superposed to the interference pattern. We are told that the slits are separated from the screen by 1 meter. So that's our L, 1 meter. We are told that the wavelength of the screen light is 500 nanometers. And we are told that the length of the arrow in the picture, this yellow arrow here, is 10 millimeters. That's our scale. And the first question is to find the slit separation. So now, knowing that the length of the arrow is 10 millimeters, we just count how many fringes we have between the ends of the arrow. For example, I count this as 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. So we have 19 interference fringes occupying the 10 millimeters approximately. Thus, the fringe width, or delta y, is given by 10 millimeters over 19, as we see it here, which comes out to be 0.53 millimeters. Now, to find the slit separation that they are asking us, then we use the expression for delta y. The expression for delta y is delta y is equal to lambda L over D. Lambda being the wavelength of the light, L is the separation from screen to slits, and D is the separation of the slits. So when we rearrange that equation, we get D equal to lambda L, as we see here, over delta Y. So we just plug in the number and get our D, which is in this case 943 10 to the minus 6 meters, or 943 micrometers. Part B of the question is asking us what expression is used for finding the position on the screen relative to the central maximum of the third order interference maximum. Okay, now the expression for the position on the screen of any maximum is given by this expression for interference. It's y sub n and lambda L over D. Now, the nth order maximum relative to the middle is given by y sub n, using n here for the order. So the third order interference maximum in this case, we just plug in n equal 3 for it. 3 lambda L over D. And we just solve for it. The next question, what expression is used for finding the position on the screen relative to the central maximum of the third interference minimum? Okay, now this is our central maximum here. So it is asking for the third minimum. This is the first, this is the second, this is the third. It's asking for the third. Now, the expression for any minimum is given by this. Y sub n is equal to 2n plus 1 times lambda L over 2D. 2n plus 1 times lambda L over 2D. Remember, lambda is the wavelength of the light, L is distance separating screen from slits, and D is the separation of the slits. Now, the first minimum occurs when n is equal to 0. When n is equal to 0, 2 times 0 is 0 plus 1, so we get here 1, and y sub 0 gives us lambda L over 2D. The second minimum is going to occur for n equal 1. The third is going to occur for n equal 2. So this is not the same use of the order as we used for the maxima, because n equals 0 gives you actually the first minimum. So we just plug it in using n equal to 5 lambda L over 2D and solve for our answer. Now the next question is, what expression is used for finding the angular position of the maximum? Now, angular position is given by this expression, d sine of theta sub n is equal to n lambda. Remember, this expression is equivalent for interference to the top equation here, y sub n is equal to n lambda L over d. The bottom expression, d sine theta is equal to n lambda, gives us the angular position, theta sub n. The top equation, y sub n is equal to n lambda L over d, gives us the position on the screen. That's the difference between them. And for small angles, which is the case for double slit interference, these two expressions are equivalent. We can use them interchangeably. Now, depending on what we are being asked. If we are asked for the y position, we use n lambda L over d. If we are asked for the angular position, we use d sine theta is equal to n lambda. D sine theta is equal to n lambda is the more general equation for interference. It is the one that we are going to use the most often, irrelevant of whether the angle is small or not. Y sub n equal to n lambda L over d is correct only when the angles are small. Okay, now going back to the question, so they are asking us for the third order. Third order is when n is equal to 3. We just plug in 3, so we have d sine of theta sub 3 is equal to 3 lambda, and we solve for theta sub 3, that's sine minus 1, or arc sine of 3 lambda over d. And we can find our angle. And you notice here is a tiny angle as we expect, 0.09 degrees. Question E is asking us for the expression for the third order interference minimum. Very much like we did with the interference maximum, we are going to use the equation for the interference minima, which is d sine of theta sub n is equal to n plus 1 over 2 times lambda. Again, the first minimum occurs for n equals 0, the second for n equal 2, the second for n equal 1, the third for n equal 2, and so on. So in this case, since they are also asking us for the third interference minimum, we just plug in n equal 2 and solve for it. And in this case, it should come out to be 0.076. And as you notice, first minimum, second minimum, third minimum. Now, this is the central maximum, first order maximum, second order maximum, third order maximum. And of course, the third order maximum comes after the third minimum. And that's why you find the angle here as slightly larger, 0.009 as opposed to 0.0076. The next question, what is the approximate width of the central diffraction maximum? Now for the diffraction maximum, if we look at the diagram, it's approximately from here to here. This is where the interference patterns are not bright anymore. So we need, using the scale, knowing that this is 10 millimeters, we try to measure what this is. Okay, now the way to do it can depend on you. Personally, the way I did it, since I know the width of each of the fringes, I just counted how many fringes are between the two red arrows that I added here. Now, in this case, we say we have about 10 interference bands between the two red arrows, so the width of the central maximum is 10 times 0.009, 5.3, so it's 5.3 millimeters. Now, question G is asking us about the width of subsequent diffraction fringes. The central maximum is what we just found, 5.3 millimeters. All other fringes are approximately half as wide. Actually, it's not correct for all of them, but it's approximately, to a certain approximation, we can take them at about half as wide, which is 5.3 millimeters over 2. Then the last question is asking us to find the width of the slit. Now, the width of the slit, since we know the width of the central maximum, we use the expression that gives us the width of the central maximum, which is delta y twice lambda L over A. A is the width of the slit. Remember, we use A for the word aperture. So it is the width of the slit in this case. So we just solve for A here, and that's what we get.